All right, great. Well, thanks everyone for joining today. We'll have kind of a 1 hour kind of completion. We'll talk about the topologies and deformation, bit of 3D volume visualization. But before I begin, I'd again like to acknowledge the traditional owners of the land from which I'm broadcasting. At the moment, I'm here in Seven Hills at home on the Darug country. So I pay my respects to their elders, past, present, and emerging. Welcome all. Thanks again for joining us. Again, I'd like to huge shout out to AuScope, who've been very generous in supporting GPlates development. And yeah, so today, I guess it's like the whole cast. You know, this is we've got everyone today. But the second hour really will be led by Ben, Nicky, and Chris. So hopefully I can finish in that hour. So let's move through. So one of the biggest advances that GPlates has been able to make is to move beyond this very simple idea of continental drift principles of just individual terrains floating around, rotating freely, not really being able to consider what the plate motions that might be required, right? Because plate tectonics is essentially this requirement to have a kind of a conveyor system. And so the huge innovation in GPlates was this was back in 2012 that we introduced it, is this idea that you can digitize lines. And for example, this line could be a subduction zone. You could have a bunch of transforms. This could be some mid-ocean ridges offset by some transform faults as well. And each one of those lines can have, say, its own identity. It could have its own plate ID, and therefore it can move independently. And in GPlates, what we can do is create topologies. So we can just say, okay, I want all of these lines to participate in that topology. And what GPlates will do is reconstruct those lines through time according to those plate IDs and Euler rotations, and then automatically regenerate that topology through time. And then, of course, you can use that topology to look at things like plate boundary, lengths, subduction zone lengths. You can then look at the velocities across that entire plate. And you can look at things like convergence rates or seafloor spreading rates very accurately, much more easily than was possible before, because in the past, you would have to digitize each plate, and then you go to the next time step and then digitize those plate boundaries topologically again, which was really such a pain in the butt. So this is the sort of stuff that you can do. Okay, you've got the plate reconstructions. We looked at the ability that we can have these plate boundaries that are these thick lines. This is visualized in generic mapping tools. That gives you a little bit more symbology, but you can see how the velocities can change across the plate. We can look at the speeds, plate velocities. That helps you understand those Euler rotations and Euler Euler poles and so on. I'll share this PowerPoint pack with you, so the animations, if you want to use them. I'll just I think there's a bit of feedback. Okay. All right. Yeah, so we've deployed it looking at, for example, like the deep carbon cycle. One thing we can do here, the different shades of blue indicate the subducting plate volume, the slab flux, or say you can look at the subducting plate areas instead and kind of estimate, well, how much sediment is going down. And this is increasingly being used to look at things even like mineral exploration. But I mentioned as well, it's still also evolutionary biologists are looking at connectivity between land masses and so on. So there's lots of different users applications. We can link these things to the geodynamics, the mantle connection models, for example. Lots of people have been doing that, and you can essentially test n-member plate reconstructions by predicting the mantle structure at the present day and comparing that to things like seismic, tomography imaging of mantle. that gives you some of the things that we do is, things like look at the dynamic topography that's implied by this convection. So that's how we can use these topologies, and I'll just start demonstrating that as well. So if I just open GPlates, again, a pretty bland, boring screen that you see. And if I go to applications, GPlates 2.3 and the GeoData, and again, just open up that data bundle for novices, right? So I can just do that, drag that on the globe, and it will load up a bunch of files. I'll show you also, just so that a few pro tips. One of the ways you can figure out where those files are that are being loaded is if you just hover over them in the Manage Feature Collection. So if you hover over any one of these, it gives you the location as well. And so you'll notice that they live in the GeoData feature collection. So for example, there's some, the rotations, the plate topologies, or, dynamic polygons, whatever you want to call them, and so on and so forth. Okay. Now, as I mentioned, it's really important to try to keep, these files together. Mixing and matching files can cause artifacts. So definitely just be careful. If you see some weird behavior, just check the set of files that you have. For example, if I load in this file here, the plate boundaries file, and if I load it in again, GPlates will freak out because it will detect all these like duplicate feature IDs. Okay, so just keep that in mind. So if I just say or hide the ridges and isochrons, what you should be able to see are these black lines. I'll make them thicker so that we can actually visualize that and see it better. Okay, so these are the plate boundaries, and if I go back in time, you can see that the plates themselves evolve through time. There's the Nazca plate. Okay, and you can see that the individual segments can move on their own. Now, so this is the most important thing with the topologies in GPlates, is that essentially, we have these models that go back to, say, 1 billion years. And to create these topologies, there is still some manual work involved, and I'll show you that in a moment. But the topologies are only accurate at the 1 million year integer ages. Okay, sometimes you can get lucky and you can, end up, oops, maybe not that far, 28. Yeah, so you can go to some other time and it'll be fine, but if you just scroll through, whoops, if I scroll through, sometimes these topologies can break at random times. Okay, so we've tried to minimize those problems, but yeah, definitely most reliable is to stick to the, integer ages. Okay, so that's the idea. But if here's another pro tip. You can, up in the top menu under View, you can go to Geometry Visibility, and here you can control the visibility of different geometry types, right? So you can here just hide just all lines or all polygons. If I hide all polygons, it will hide, the coastlines and so on. But actually, what I want to highlight is these topological line sections. So I'm just going to show everything, and then I can also activate them in the layers dialog. Okay, so you can now see this kind of messy set of lines that can intersect each other. Okay, and so there's one line, here's another, and here is another one of these, and you can see GPlates will pick the middle segment of those intersecting lines. Okay, now what you can do as a user, you can of course digitize your own lines. Okay, so say you want to put in a subduction zone here that could, I don't know, say represent the Eurasian system, 100 million years. Oops, plate ID is 301 for Europe, Eurasia. Say from 100 million years to the present. Okay, so here's a new plate boundary I've just created. And to create a plate polygon, it's fairly straightforward because you just activate this topology tool. Okay, you can make line topologies. I'm not going to go into that today, but you can look it up in the tutorials. And you can also create these rigid plate topologies and also deforming topologies, which I'll talk about a little bit later. And the way that you do it is you choose any one of the lines, and then you add them sequentially going either clockwise or counterclockwise. Okay, so for example, I can just click on one of these lines. I can say add, select the next one, click on add, and then just go, like I said, you just have to make that decision whether they go, whether you want to go clockwise or counterclockwise from the beginning. Okay, and I can click on create, just to use that topological closed plate boundary. You click next. This is where you need to specify the plate ID. In this case, well, it's India, so it's 501. So you need to be able to, I guess, identify what plate IDs you're dealing with. Put in the begin end times, and you can put in the name, for example, and then we can just put that in the new feature collection. So one of the things I can do now is, just highlight to you what happens is that GPlates will intersect all of those lines, okay? And it means that if I create any velocity domain points, like we did the other day, just always make sure that you set the output directory. Okay, GPlates will be able to read those velocities. And so the reason why right now it's reading a lot of the other ones is by default, it looks at all of them. Okay, so you can see that it's happily reading those velocities in here. Now, as I go back in time, you can see that, well, those lines move independently. Okay, but then at some stage the topology breaks, and the reason why it breaks is because some of those lines have disappeared. Okay, that boundary that you can see here, it has an age range from 83 to 71 million years ago. Okay, so we go forward in time, you see, oh, it breaks. Okay, the cool thing about GPlates is now I can say, well, I'll take this, malformed topology, and I can edit it. So I can just show you. So here you can select a topology, and then you can make edits. So hang on, that's this button here, or you just press E on the keyboard. And again, the details, I recommend that you look at the tutorials, but what I can do is select the insertion point, and the way it works is it is determined by these colors. Let me just hide, again, those ridges and isochrons. Okay, the insertion point is between the blue and the green line. Okay, so for example, okay, I see there's a problem here. There's a gap. There's what we call this rubber banding artifact. There's no intersection. GPlates freaks out and can say, well, okay, I click on this one line. Okay, and then it's the one next to it, and I can just move that insertion point. I think I can just press this arrow. Okay, you can see how they become blue and green now. I can select this line that connects them, click add, apply, and it fixes that rubber banding artifact up here. There's still rubber banding artifacts down here. Again, easy fixes. I can activate that edit tool. And this time I want to insert some lines between this line and this one here. You can see these dark gray items. These essentially are the things that have disappeared. They no longer are active at this time. So I can change that insertion point, and always you want to add from blue towards the green lines. Okay, again, replicating that counterclockwise thing, but you can never really remember. So I always just remember it's blue to green. So I can click on add. Just keep adding these topologies. Click apply when you're ready. Okay, and then you have your updated topology. So this is essentially how these plate topologies work. The really cool thing about that now is, I don't have to mess around with, editing the neighboring topologies. I can essentially edit individual lines, those plate boundaries, and GPlates will on the fly recalculate that topology here, okay, as well as its neighboring plate as well. Okay, so I'm not really sure how many people will be making use of this, but it is pretty cool to look at the kinematics, and when you're building actual true plate tectonic reconstructions, you want to look at what the actual plates are doing. Okay, great. So I'm just going to answer the question from Chris. Chris mentions it'd be useful to have an option in GPlates to visually differentiate between features that are fully or largely observational, factional or fictional, and features that are largely based on modeling could prove to be fictional. Yeah, so Chris, I think that's a broader, I guess, philosophical question on one hand, but it's also a technical question too. There's so many cascading inputs, and then of course, you've got your magnetic anomaly identifications, which carry some error uncertainty, and then the definition of many of these plate boundaries, particularly in the synthetic seafloor that's been lost to subduction, right? So there's, as you say, like there's different levels of certainty or fantasy. It's something that we've been thinking about for years, and it's just very difficult to actually tag which areas of the globe have different levels of certainty or uncertainty. I think, but I totally agree with you. This is something that I'm also working towards. That it'd be good for a user at least to have an idea. Okay, which parts of the world are completely synthetic and made up, and then which is well constrained and which is in between. So for example, here we've got the Pacific plate, and if I go forward in time, a lot of this area has been subducted, but you can assume seafloor spreading symmetries and resurrect some of that plate. Okay, whereas if I go back to say 240 million years ago, I keep going back too far in time, then we get to say Panthalassa, right? And this is entirely synthetic, and we don't really know what's going on. So definitely room for improvement there, Chris. Okay, Peter asks, can you change the line styles like dotted, dashed, rather than just solid? Again, in the current version of GPlates, you don't have that control, you don't have that symbology, but that will come with the next major release that will have symbology. So that's definitely on the cards. And so yeah, with that symbology, what I typically do is I use generic mapping tools to plot, and there I can control all sorts of things. I can plot the subduction zone polarities and so on. And Ben and Nicky will show you some pyGPlates, so Python stuff as well. But yeah, just going along that question, you can, yeah, you can export those resolved topologies, those plate boundaries. I think we played around with that on, I think, even day one. So if we go to reconstruction, export, one of our favorite menus. Okay, in that export section here, I can export those resolved topologies, which are those plate boundaries. Okay, many of you might be using GIS, and so you can get some nice, useful plate boundaries that you can use. Okay, and again, just remember that GPlates makes it very easy to change the anchored plate ID. But if you're exporting these different components, make sure that everything's being exported in a common reference frame, whether it's an anchored plate ID of 0 or whatever you're looking at. Okay, and just as a recap, those velocities, they can be sampled from, by default, they're sampled from these topologies, okay, plate topologies, but you can connect up to any other, what we call static polygons that don't change their shape through time. So let me just hide some of this stuff so you can see those plate boundaries evolving. Okay. All right, so that's the plate topologies. Are there any questions on the plate topologies? No? Okay, excellent. So let's talk a little bit about deformation. And while the next thing I'm going to load will take a few minutes to load in GPlates, so I'll start loading it and then jump into the PowerPoint. And so that lives again in that GeoData feature collections, deforming lithosphere, and then there's a couple of things here that are quite important. There are 2 project files. Make sure that you're loading, for now, the low res version. That takes a couple of minutes to load. The high res version, I believe it can take 20 minutes, 30 minutes to load, because there's just so many points that need to be considered. So again, I'm just going to load in that low res version, and I'll talk about deformation a little bit. Okay, the deformation is an extension of that topology philosophy, right? And it's the first software like this that is essentially deployed it and can capture and track deformation. And the way it works is it's quite similar to those rigid topologies, right? Because what you can do is create the outside boundary of these deforming regions. And again, each one of those lines or points, or what we call these topological lines that are made up of individually moving points, you can connect them up just like we did before, right, to create the boundary. And then you get some what we call triangulation across those points. But then what you can do, which is really, 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 really cool, is that you can add to the interior of those deforming networks things like, individual points that can move independently from each other. You can put in polygons, which are, say, rigid features, like cratonic, very rigid features, like the Tarim craton, and you can put in sub-basins, I guess, that can move independently. So just like before, just to highlight, is that each one of these features can move independently, and GPlates will on the fly compute that relative motion, that triangulation, and figure out the strain and deformation. So the way that we've created it currently is that, okay, we've got the COB, the limit of bona fide oceanic crust, and then we have another line which is the unstretched continental crust limit. Okay, and in between we assume that there's been deformation on these margins. Okay, and you can build these sorts of topologies that you can see here. There's lots of points, and the different colors indicate well, different sorts of behavior. So the blues are extension, oranges, reds are contraction, and you can track that through time. Okay, and you can see how that evolves. You can build some pretty complex reconstructions. The one thing, the caveat currently is that it's kind of a, well, it's a pure shear uniform extension model, but there is some emerging functionality in GPlates that we're testing, which is essentially allows you to focus deformation, make it more realistic. Okay. The cool thing about the GPlates functionality right now, this feature that just came out in GPlates 2.3, is that, well, you can track things like the crustal thicknesses through time. So say you have your initial crustal thickness at, you know, 40 kilometers, and then you can track the, well, you can track the stretching factors, the crustal thicknesses through time. But also in 2.3, what's come out is the tectonic subsidence. And the tectonic subsidence curve or you know, evolution at each one of these points is the syn rift, the stretching related subsidence, but also we've got the post-drift thermal subsidence that is being tracked, which is quite cool. I think that might be useful for some people. So I will, let's have a look at this in GPlates. So I've loaded in that project file. Okay, so I'm just going to make this a little bit smaller. Okay, come on, my mouse is not really reacting very well to me. Okay, great. So if I go to say, I don't know, 200 million years ago, well, really, I think it's 240 is when we populate these deforming networks. And if I play that forward in time, you'll see the colors start to change. Okay, and again, in your layers dialog, you get a new option, this kind of gray layer, and you can choose. Okay, you can choose to be looking at the crustal stretching factor, or the crustal thickness, crustal thinning factor, or the tectonic subsidence that's implied. And I'll explain to you how to make this stuff from scratch, but it's useful to you know, kind of look at what exists right now. And again, we have this kind of inbuilt color palette for the crustal stretching factors. Any value between 0 and 1 is contraction, and then anything greater than 1 is extension. Okay, so it's time integrated, but there are ways to extract, you know, I guess the instantaneous strain or whatever, right? Okay, so you can see how that evolves through time. And GPlates will track, will deform those points. So if I go back in here, you can see those triangulations, and then those points are being deformed very efficiently by GPlates. Okay, you can track that through time, say to the present day, right? And then, yeah, you can look at things like the tectonic subsidence through time. Okay, so I can just change that drop down, the scalar field, and then the units here are in kilometers. It's also cool because you can export those things through time as well, right? So you can, again, go back to our favorite menu. If you go to reconstruction and export, let's just say, I don't know, 200 to 0 in 10 million year intervals. I can click on add export. And here, the key thing is the scalar coverages, okay? So they are those points that are carrying all that information. The deformation here is some information of the deforming networks themselves. So you can play around with that, have a look. It can output things like the, you know, principal strain, stretch, the dilatation, strain, the you know, things like even the strain rate style, you know, from the Creamer papers that tell you, well, is it extensional, compressional, you know, tensional transform kind of motion. Okay, So that's kind of cool. But yes, the scalar coverage is if we can choose, yes, so the GMT output. Let's just say, well, export to single files. You can export additional options here, but in this case, it will export the longitude, latitude, and also the scalar field, which is whatever you've selected. I think we have the tectonic subsidence. So click OK, select the output directory, and click begin export. You can see it's really quite quick. Okay, so I can just grab one of these random ones and okay. Right, so it tells you, some information. So what the reconstruction time is, the anchored plate ID, just so that you can remember the name of the, I think the topology, and then these are the points. Okay, longitude, latitude, and the tectonic subsidence value at that time. All right, so lots of things in here. You can of course grid that up, interpolate that, and so on. Okay, now what we can then do, I wanted to show you how to actually make these things yourself. Okay, so I'm just trying to think of, well, what's a good place? What's a good place to look at? Okay, so we keep coming back to Australia, Antarctica. Let's come back to Australia, Antarctica, right? Like I mentioned before, you can make these deforming topologies really easily. Okay, let me show you the topological sections, and I'm just going to show you a toy example that we'll discard when I'm going to use. But it's okay. It's that topology tool, the build new network topology. Okay, rather than that rigid topology. And again, it's very similar. So you click on add to boundary. You choose whether you want to go clockwise or counterclockwise. Let's just say, okay, I want to go counterclockwise. This is going to be a bit crazy, but no, actually, let me choose somewhere else that's a bit more straightforward. Well, let's stick to Australia. Okay. So yeah, it's just a bit more difficult to click around here. So one of the things in GPlates is when you click, you want to select that line, for example, it will highlight whatever things on top, but you can use the bottom panel here to isolate these things. Let me just make sure that everything is shown. God, there's so many lines. Yeah, the coastlines are on top of everything, which makes it hard to see. Okay, so there's like a COB segment. So let me just start creating topology, add to boundary. And there it is, add to boundary. And gosh, there's lots of individual points here. I don't have the time really. Add to boundary. And so on. It's very similar to what we had. And I'll just complete that. So yes, I just create a new topological network. Again, you want to give it those age ranges, a name if you like. And the interesting thing is that these topological networks don't really have to have a plate ID. You can put in a plate ID in there. It's kind of like a backup in case the points that are in there, they get jettisoned if the network disappears. But if you give it that plate ID 801, sometimes yeah, it'll help reconstruct those points to the present day. Now, so I've created this topology now just to show you. I don't even know where I've put it, which layer. There it is. Okay, it's a terrible topology because I haven't closed those things properly, right? But it's just an example of how it works. Now, once you've created your topology, as I mentioned, you can add in internal features, any faults, any points, or any rigid blocks that might represent undeformed crust. So I think what I've done here is I've just I'm showing everything. I think it's just reloading it from scratch. So that's fine. We'll let it think. And I just want to see if I do have an example video somewhere. Okay. Okay, so here I'm creating topologies, right? Changing them through time, looking at Greater India, for example. Okay. And once I'm happy with those topologies, I can essentially drop a whole bunch of points on there. Okay, and I'll show you how to do that in a moment. So to do that, you just need to select your topology. This is just showing you can put in these rigid features. Let's see. Let's go back to GPlates. Is it? Yes. Okay. It's there. It's awake. That's good. But I do actually want to hide it again. This is unfortunate. Okay. So let me just eject this feature I've created. Okay. So what we want to do is go back to the beginning time of this deformation. So it looks like it's 136 million years ago. I just want to go back a few more time steps. Okay, so it looks like I've just messed up okay. So it looks like it goes all the way back to 160. Okay, so 160 is when that network starts, and we can say, okay, that's pristine, relatively uniform crustal thicknesses. I can select that deforming topological network, okay? And then it's really easy to populate those deforming points. So if I just go to features, generate deforming mesh points. Here it's what I recommend is always using this focused feature boundary. Okay, so it just uses the extent of this polygon to create these points. This is the density level, so you can play around with that. It just tells you approximately here what the spacing is. But yeah, let's say I choose 7. I click next. This is where you can set that initial crustal thickness, right? Say, I don't know, you had very thick crust. Again, the plate ID is not that important here. But yeah, this is important, that initial crustal thickness. It doesn't matter too much because GPlates primarily tracks the stretching factor. So you can ignore this as well. You can apply your own thicknesses as a post-processing thing too. Next, click create. You then get some additional options. Most of the time, you just want to leave it as default. One option that I sometimes use is you can deactivate points that kind of get fall outside of the network, but it doesn't really matter. So you can explore those options a little bit. Okay, so it's created a new layer, and you can see there's that scalar type. You can explore that. Tectonic subsidence, stretching factor. You can change the color palette to anything you want, right? And then if I play that forward in time, and what I'm going to do is I'm going to set the anchored plate to be Antarctica. That's probably unfortunate because it's even though the other layers are hidden, it's probably going to try to rotate all the other deforming points, the global ones, just fine. It'll take a take a moment. There we go. It's not that long. Okay. You can see that there's deformation happening. Okay. If you're not seeing the colors, it's let me just again make those points much bigger. And I can constrain that color palette very easily. And you can see those deforming points in there. Okay. And again, we can see what the crustal thickness and ends up. You know, you've got your 60 kilometers, you know, undeformed crustal thicknesses, and you get those extended pieces of crust. Okay, does that make some sense? Maybe, yeah, from the recording, you can follow along a bit more slowly. I just don't want to eat into the pyGPlates at time. But, you know, might some of this be useful to some of you here? I'm curious if anyone's interested. Ricardo is interested. That's good. Mohammed, how does the software know whether to stretch or thicken the deformation? Yeah, that's a really good question, right? The way it knows is that network or that topology that you've created, right, is made up of these individual segments. So let's have a look at this figure again, right? So you've got all of these individual segments, right? And so GPlates, what it does is it creates a triangulation network between all the points there, right? All the geometries. And if it detects that there's relative movement between them, right? Okay, so if there's an increase of distance between them, it retriangulates and it realizes that there's a greater distance, and it then propagates that to the points, right? So it stretches the points. And so similarly, you know, if there's convergence between the different geometric elements, then it pushes things together and it causes compression. Okay, so hopefully that explains that. And Karen asks, yeah, so how far back in time does it go? The current model that we've publicly released and it's published in a 2019 paper, it goes back to 240 million years. So it captures that kind of Pangea breakup history. We're still filling in gaps and, you know, taking it back further, but you know, it was our first attempt, and I know some others have kind of built on it and you know, looked at particular regions in greater detail, you know, adding in these rigid blocks and refining some of these things. And of course, you know, when you put in the different motions, remember that interactively in GPlates, you can just move things around, right? You can move them around, so you can actually create your own deforming points. Jamie asks, is the thickening and thinning proportional to the extension compression then? Yeah, so this is, yeah, it was just pure pure shear. So it's uniform stretching or uniform thickening, but there is functionality. I think it's explained in the manual, and maybe even I thought we updated the tutorials as well, some kind of new functionality that we're testing that allows you to focus the deformation to have, I guess, a gradient of extension. Okay, so I mean, at the very least, like I said, for teaching, it just helps students visualize, you know, that, okay, different places in the world they've had stretching. Southeast Asia is really cool, interesting that you've got you know, you've got stretching and compression simultaneously, and it just highlights, you know, particularly to students, that, okay, you know, the continents can deform quite readily, you know, oroclinal bending, all this sorts of stuff that you can explore as well. Of course, anyone looking at basins, you know, to look at the subsidence history can be quite interesting. All right, excellent. Thanks for all the questions and comments. It's nice to know what people are might be using. So Pei asks, for each polyline composed of the topology, the points we draw each polyline will affect the geometry of the mesh triangle, which will affect the deforming points, such as the crustal thickness over time. My question is, how much difference we draw the points for the same tectonic element in different ways? Yeah, so Pei, you ask a good question. Yeah, so as you say, it is somewhat important how many points you provide to that line for that triangulation. So if I zoom in, I choose one of these lines, okay, and well, let's just say I want to edit, sorry, where was it? Okay, I just want to move those points. You can see that the triangulation is limited to those points. I mean, I can add more points. GPlates will then re-triangulate and will reform those meshes. I don't think it makes a huge difference. I don't think you should go like overboard, but you should have enough detail that captures, I guess, the geometries that you're looking at. If you're looking at very fine scale, small regions, then it becomes maybe a bit more important to do that. Okay, but as you can see here, that it's probably more efficient to do that at the very beginning, when you create those geometries. Then like, okay, I've got all these points, I've got all the deforming scalar fields, and then okay, then you edit the line, just add one point. Now GPlates is like, okay, it's adding that point, it's retriangulating, and it's then propagating any deformation through time. Okay. Hodget asks, can we extract different attributes of features based on a specific feature? So obtaining convergence rate, subduction angle, age of subducting seafloor. So that's for the next pyGPlates component. So I'm going to leave that for Ben and Nicky. Geo asks, how does it understand the viscosity for calculating deformation and thickness? Viscosity is important. So yeah, that's a good point. There is some technical papers. I think it's based on some of the McKenzie models and work. And you can look at that in the original 2019 paper. And if you've got any questions, you can put it in the forum, and John Cannon can clarify as well. Ricardo, so if I understand, the deformation is occurring at plate boundaries, or is intraplate deformation extension shortening available, or do we have to generate those? Yeah, so Ricardo, yeah, I mean, that's a good question as well, right? In GPlates, traditionally, when you create those rigid topologies, everything is treated as a rigid tectonic plate, right? So it's not, there's no there's no particular concept of deformation at the plate boundaries, right? I guess there's subduction at subduction zones. In this case, what you can do is you can add in regions of deformation. I mean, you as the user, you have to add them in, right? You have to decide what is the extent of the deforming regions, what's rigid and what's not. So if I go to say 40 million years ago, there's Southeast Asia. Okay, let me just change this. Tectonic substance is not very useful here. Stretching factor. Okay, so you can put in rigid blocks. You have to decide essentially where that's all happening. Okay. Yeah, so Yudu asks that yes, the initial crustal thickness that you impose essentially is uniform, right? And that's why I said like that may not be so useful for you, because of many regions have variable crustal thicknesses at that initial point of deformation. Okay. So you can use the stretching factors instead to apply any crustal thicknesses and just figure out the change in. So you can, for example, give it the present day crustal thicknesses of your region and combine it with these stretching factors to, I guess, recover what is the implied original crustal thickness. Okay, hopefully that makes sense. I hope that makes sense. Okay.
I think there was a question further up that I think you missed.
Sorry.
How does it understand the viscosity for calculating deformation or thickness? Yeah.
So that was that was my response, in the sense that it uses the Mackenzie style models. There's some specific papers on this that look at the I guess the viscosities and densities and so on of the lithosphere, because like it is important. You need to consider the lithosphere as well, particularly in that post-drift thermal subsidence. So those details are there, and in the paper, the 2019 tectonics paper, and then also you can ask in the forum. John will answer. Okay, great. So we have a grand total of 8 minutes, which won't give us a chance to go through in depth the 3D visualization, but because I've had some caffeine, I can do it in 5 minutes. So, so hang tight. Put on your seatbelts. No, it's not. It's yes.
Sabin? Yeah, sorry.
Yes.
Mohammed also asked for a demonstration of the pole of rotation calculation. Is there somewhere we can point him towards, maybe, if we don't have much time?
Yeah. Look, I mean, the pole of rotation, it's a complex issue, right? It depends what you mean, because GPlates will compute those poles of rotations and write them out to the rotation file. But I suspect this is about visualizing it in GPlates, and that's a bit harder. And I think I mentioned that was I think if you look at the tutorial related to paleomagnetism, it does cover some of that, but it may not be essentially what you want, to be completely frank, because it's in the paleomag, it's important because the radial symmetry of the magnetic field, you want to be able to move your terrain longitudinally, any longitude, but keep the latitude constant. So have a look at that, Mohammed. But if you get stuck, let me know. Okay, now the 3D volumes in GPlates are great. They will become even better in the next releases of GPlates, because you'll be able to tilt the view better than you can at the moment. But the way that they work, it's really quite straightforward. Is that I mean, most of you are probably familiar with what we call net CDF grids, and they usually have an extension of .nc. Some of the older files that we provide, others provide .grd. Jono has been dealing with this for the last few weeks, but anyway, these are numerical grids, so depth slices of P-wave tomography. And to make it work, you just provided some grids that have a consistent region, right? And then in the file name at the end, I think after the underscore or a dash, you put in the depth in kilometers, right? So this is going from 50 kilometers depth all the way to the core mantle boundary. And so to import your own, you can just go to File, Import, and then Import Scalar Field. Okay, you can click on Add Directory or Add Individual Files. Let's just say, let's add individual files. I can select these files, just drag them onto this dialog, click Open. And so, GPlates will create these, cache files like we discussed before. It knows what region they're in because of those net CDF grids are, they have some region. Okay. And then let me just hide a bunch of things. Then you get a layer at the bottom, this kind of dark green layer. Where are my coastlines here? Okay. And if I expand that layer, it gives you lots of options, right? So first of all, the default is that you just have an isosurface. If you're looking at, say, tomography, in this case, if you just want to look at slabs, well, you want some kind of positive seismic velocity anomaly. And you can, put in some contour, positive contour here. The colors here indicate depth. Okay, so yellow is uppermost mantle, orange is kind of mid-mantle, and red is lowermost mantle. So it can be a bit deceiving. This doesn't mean hotspot plume. You can choose to color it just by a single color. Where is that? Hang on, let me just make my screen a bit bigger. Yep, so you can just use the color mode, just the scalar, and again, you can apply your favorite, tomography color palette. Okay, so similarly, you can, okay, you want to look at the upwelling. Oops, 0 point. The hot spots. And of course, you can apply different color palettes. So there's Hawaii, there's some other things here. And again, the color is not very good in this case. Let's see. Okay, let's choose something a bit more appropriate. Okay, so this is all fine because you can reorient the globe, but currently you can't like tilt the view and change the camera angle, which is a bit frustrating. And that's going to be in one of the coming releases of GPlates. The other really cool thing that you can do is have what we call this double deviation window, so you can simultaneously visualize the slabs and the upwellings. And of course, you have to be careful with your color palettes. I think this is generally okay. You can play around with those contours. Okay, so and there is a whole tutorial on this stuff as well. Here I've just chosen a very kind of low resolution tomography model in the GeoData, and on the EarthBite website I have included, so if I go to scalar fields, I've included the say the MIT P-wave tomography for Southeast Asia. So it is higher resolution. I think I provide also the global version of this as well. Again, just to minimize the file size of that GeoData. Okay, so this is a Java Sunda slab here. So the last thing I want to demonstrate just very quickly is that you can also digitize cross sections. You can make them as complicated or as simple as you want. So if I just digitize something, line, create the feature, doesn't really matter what kind of feature it is or its plate ID, doesn't matter, just as long as it's there. I can then, in my 3D scalar field, this 3D volume, I can choose this cross-section method, okay, and I add a connection to that line that I've just digitized, okay, and there is that cross-section. You can change the color palettes. You can muck around with that, okay, and so yeah, there's the Java Sunda slab. And one of the cool things is, okay, I mean, the tilt of the camera is a bit annoying, but you can modify the position of the cross section interactively. So it can allow you to explore the tomography a bit. So for example, for me, where is the Proto South China Sea slab? And here I can say, okay, it looks like it's somewhere here. Okay, so that's some yeah, some basic kind of interactive visualization. You can, of course, visualize, things like the geodynamic mantle convection models and so on. But yeah, this will become a lot more useful when you have the tilt of the angle, tilt of the camera implemented. But keep in mind, you can still export this as a scalable vector graphic, so you can make some very quick figures, which is I think quite useful. Okay, so I promised I covered that in 5 minutes, and the crash course in 3D visualization in GPlates. So essentially, I just wanted to thank you all for coming along the last few days. With the GPlate stuff, we've kind of had that Q&A throughout the week. And I'm going to hand over to Ben, Nicky, and Chris. So thanks, everyone. It's been fun.
Good morning, Australia, and good evening, the United States. This part of the course is to do with pyGPlates, and we're very much looking forward to taking you through some of the fantastic functionality that's offered. So Sabin has, over the last couple of days, gone through all the cool stuff that you can do in GPlates in making the reconstructions. pyGPlates is more focused on interrogating those reconstructions. So what we do in pyGPlates is we load in your favorite rotation models of choice, your topologies, and then you reconstruct those back through time using the power of Python, which you can script with other Python plugins to create nice maps or input some data into some machine learning algorithms. There's a whole bunch of different things that you can use pyGPlates to do with these plate reconstructions. So I'm Ben, and there's Nicky, and then there's Chris, and all of us are going to help you through this journey through Python and pyGPlates. So please reach out if you have any questions, either in the chat or on the EdSTEM platform. So you should have received an invitation to join the EdSTEM platform. If you haven't received an invitation, then please send Nicky or Chris a private message in the chat with your email address, and they'll add you. But I assume that most of you have received an invitation, so that would be good. What I'm going to do now is share my screen and introduce you to the EdSTEM platform. So here we go. All right, Nicky and Chris, can you guys see my screen?
Yeah.
Perfect. Great. Okay. So once you accept the EdSTEM invitation, you should be linked to this welcome page. And here's my little post here at the top. We've already got a comment and a question, so that's great to see. So this is the platform that we'll be using during this pyGPlates tutorial. So you can start a new thread. You can categorize it. It could be a question, a post, or an announcement, all these different things. So you can ask questions using this platform. And I think that'll be good, because then other people can learn from those questions that you ask and the responses that we give. Okay, so most of you guys will have Python installed on your computer. If you haven't, that's okay. Everything is housed within this EdSTEM platform, so there's no installation requirements. You just have to have a browser, and you'll be able to run all of the course content. For those of you who are game and have Python installed on your computer, you can actually just go into the GitHub repo we created for this course and just take note of the address here. I can put that in the chat, actually. Yeah, so this is the GitHub repo, and it's got a README file here with all the notebooks. and documentation. And then here's some installation instructions for you to get started. Yeah, so, perhaps do this in your own time. There should be enough resources on EdSTEM to suit everyone. So if we're all feeling pretty happy and confident with that, then we can get started. So up the top here, this is our discussion panel. What you can do is click on the workspaces, and then down here, you'll see that I've created a public workspace, helpfully titled Workspace. So click on that, and then you'll be taken to this screen where there's a whole bunch of notebooks on the left. And if you guys just click on that, you'll be able to see some of all these different cells and stuff, but you won't be able to modify it. So to modify it and create your own version of this, you just hit the fork button, and it'll ask you if you're sure you want to fork it, and you say yes, fork, and then that'll create a fork of the repo in your own workspace. So how this works is essentially we've assembled a whole bunch of computational resources on this platform. So you get your own, I think it's like 50 megabytes of storage and up to 1 gigabyte of RAM to use within your workspace. And you can upload files, you can export graphics and stuff within your notebooks, and that'll all be saved to your own personal workspace. Okay, so then after the class, you can download those workbooks, all those files to your local computer, and you can take it with you. So we'll aim to keep this EdSTEM platform running for about a week after the course, just so you have that opportunity to dive back into the notebooks, have a fiddle around. But then after a week, we'll probably shut it down. So make sure you download everything from the platform before then. Okay. All right. So once you've forked this repo, then yeah, under workspaces, you should see, your own copy of this, and then you just click that. And then let's go into notebook 1. At this point, I should ask, is there any questions? Does anyone have any difficulties loading the EdSTEM platform? If you do have any difficulties, then please just use the discussion panel, and yeah, Nicky and Chris will be more than happy to help. So I'll run through the first notebook. And maybe Nicky, do you want to run through the second notebook?
I can run through the second.
Yeah, and then tomorrow we've got the rest of the notebooks that we'll run through. So it's exciting times. All right. There is a question. How have you fork? Good question. So what I do is I go into public workspace and I press this button here, which says fork. It's a little bit tucked out of the way, but you hit that button and it asks you if you want to fork. You say fork, and then it's done. Okay. All right, let's dive into the first notebook. So we're kind of assuming basically no prior knowledge of Python. So this is just a very brief run through to what some of the key features of Python have in store. So this is what we're using today is the EdSTEM platform. And these kinds of notebooks here on the left, they're called Jupyter notebooks. And Jupyter notebooks are pretty cool. They're kind of like a good way to kind of document workflows and analysis pipelines. And it's not just limited to Python. You can have R notebooks, Fortran, Julia notebooks. That's all possible as well. So the top cell here is actually a markdown cell, and we can double click that here to see what it all looks like. This is markdown, which looks pretty good. So you can annotate your workflow as you go. And there's also, support for equations here between the dollar signs using LaTeX notation. And if to run that again, we just go Shift Enter, or you can just, I think there should be a run button here somewhere. Is there a run button here? Yeah, Shift Enter is the keyboard shortcut. So you hold down Shift and hit Enter, and then that runs the cell and moves on to the next one. Okay, so let's do some basic stuff with Python. Okay, so Python is pretty intuitive. This is just some maths operations here. So we can, multiply and add numbers together. We can assign, whoops, what's going on here? Okay, that's quite weird. Yeah, very strange. Okay. Well, anyway, we can run numbers. We can assign numbers to variables. So in this case, we're assigning the value of 145 to time. Okay. And we can also create strings. So to print out a string, we put this print at the front, an open bracket, close bracket. And then the string part of this is actually in inverted commas. So the sample age of the sample is comma time, which we've defined earlier. And then we've got a second string there, million years. So we can print out a nice sentence like that. We can also make variables from pre-existing variables. So end time is equal to time plus 56. And if we print out end time, then we get 201. That makes sense. We can also assign strings to variable names. So geological age is equal to Jurassic. We can extend our string a bit further. And there we go. My sample is 201 million years old from the Jurassic age. Good. We can also make lists. Now lists are really important in Python. You can store basically anything in a list. So in this list, we're making a list of times. So that, yeah, times is the name of the list. That's equal to 1, which is an integer, 4.5, which is a floating point number, an operation, so 5 plus 3.2. We've also made it equal to another variable, another string, and a Boolean statement, which is just true or false, in this case, true. So we can assign this into a list and print times. And then, it's got all of these different items within this list. The other cool thing that we should be aware of with lists is that we can index it. So we can take the 0th item of this list. Now beware of this 0 here. So Python has 0 indexing. Other languages have 1 indexing. So, like Fortran, I think has 1 indexing, whereas Python has 0 indexing. So all lists start at the integer 0. Okay, so if we run this, print the 0th element in times, we get the first element in the list. And we can modify this too. Let's go times 2. And we get 8.2. And let's try times 3, we get Jurassic. We can also do sub-indexing as well. This only works for some data structures. So for strings, it works. We can subset this to 0, and then we get the 0th item of the 3rd item in the list. So we get J, because that's the 0th character in Jurassic. Okay, and another Python object, Python data type that you'd find quite frequently are functions. So these are kind of bits of code that you want to run perhaps many times, or at least keep them self-contained, so you can refer to them at different points throughout your code. And they can always take input values and give you back something at the end. So in this case, we're defining a function, which is, we declare the function name, which is def add numbers. That's the name of our function. We can call it anything we like, but I've decided to call this add numbers because what it does is adds X and Y together. So to create Z. So Z equals X plus Y. And then at the end of the function, we have our return statement, which returns the value of Z. Okay, so if we just run that, then that's now in our memory. So we've run this cell. So the function has been declared, and then we can just run this function inputting two input variables, 1 and 2. And unsurprisingly, we get the value of 3. We can change this up a bit too. So let's go. And then we get 7. Okay, so at this point, let's do a little code challenge. So what I want you guys to do is to write a function to convert map scale. So for instance, on the 1 to 25,000 map, which is good for hiking, the distance between 2 points is 15 centimeters. So how far apart are these in real life? Okay, so you just have to augment or augment this function, create a new function, which does this map scaling. Okay, so we'll just leave that for about 2 or 3 minutes. And then I'll write down the answers. So this is just a good way to kind of test out your knowledge so far in how to create functions, because you'll see functions again and again. And it's good to know how they operate. Oh yeah, the other important thing to keep note of is that everything that is declared within a function has to be indented. So this is very important in Python. Indentation is king. So everything that occurs within the function is indented, and then everything outside the function is not indented. Okay. Also, this kind of pink text here, this is just text, it's not code, but it's kind of useful to annotate your code so that other people know what's going on, right? So when people see this function, they can immediately see that there's some documentation that goes with it, whether it's input variables, what is it, return variables, and a basic description of the operation that goes on. Okay, are people feeling relative?
Does anyone have any questions? It's very quiet.
Okay, I think that's probably about long enough. How do people go? If you've got something that looks a little bit similar to this, then you're on the right track. Okay, so it's a multiplication. You multiply the distance in centimeters by the scale, and then you get your answer. So I think, let's see if this actually works. Haha. Success. Isn't that good? That claps to you if you got that right. I can't tell, but I think I think you guys are doing great so far. All right. Now let's go on to something a little bit more difficult. Okay. So the sort of covered functions, another common thing you'll see within Python code are loops. So the way we write a loop in Python is inputting a for. Okay. And then what you do is you do for my thing in a list of things. Okay. So say if we have our list, which we've defined above. So remember before, let me just add a code cell. Okay, oh yeah, that's something important. So yeah, one of the key things in this operating environment is that you can add code cells by pressing this plus button here. You can also add text cells as well, in the same thing. So let me just, and you can like click on these cells and drag them around whenever you like. Okay, so let's refresh our memory. We have defined our variable called times, and we have our list. Okay, so there's our list. And now let's iterate through this list. So for my thing in times, we're going to print out my thing. Now, a good way to kind of think about this and how for loops kind of work is like, say you have a bookshelf, which is your list. And essentially what you're doing is you're taking each book, so each item from the list off the shelf, doing something with that book, then returning it back on the shelf and then picking up the one next to it, okay? So that's how lists kind of work. You have a list of different variables, and within that list, you're taking each item and then doing something with it before going on to the next item. So what we could do to strengthen this analogy is make times equal to bookshelf. And then for book in book shelf print book. Okay, and then I've just changed the text in here, but it's doing exactly the same thing as before, right? So each book in bookshelf is equal to each item in that list. All right, let's not dwell on that too much, but we can also extend this. So if we want to keep track of our index throughout that list, so what we can do is pass this enumerate function around times, and so that keeps track of what the index is. So before we had for my thing in times, we've also got index. Okay, so what I'm going to do here is run this cell. So the 0th index in times is 1. Yeah. The first index in times is 4.5, second 8.2, etc. Another thing that you'll see quite frequently in Python is control statements. So here we've got time equals time is equal to 145. So if time is less than or equal to 200, then we can print Jurassic age. Or else if time is greater than 200, then we can print Triassic age. And if it's none of those, then we can do something else. In this case, we don't do anything, we just pass. Okay, and then we can change the value of times. So let's change it to 250. And it's going into Triassic age. All right. Oh. Okay, 100, let's change that back to 145. Perfect. And we can extend this out quite a bit. So here I've actually nested these conditional statements into a function. So remember, the function has def out the front. Perfect. And then our function is defined as time scale, and it receives one argument, t, which is our input time. Okay, so I just run that cell, and then so I've defined the function in memory, and I'm going to pass an argument to it, which is just 1. Okay, and so 1 is defined as, it kind of traverses this whole tree of different conditionals before it gets down to this one here. Okay, so in all of these, each of these statements is false. So false, 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 until it gets down to here where it encounters a true statement. And then it returns Cenozoic. And that's what happened. Okay, keep those questions coming. Yeah, I can't actually bring up the discussion board at the moment, but yeah, if Nicky and Chris could have a little look at that from time to time, that'd be awesome. All right. Okay, so we've kind of done a fair bit in, what is it, 27 minutes. Now we're going to go on to NumPy data structures, or NumPy data structures. I don't know what the lingo is on the street. Do you call it NumPy or NumPy, Nicky?
Call it NumPy, because it's like, then it's Py like Python, but that's just me.
Yeah, no, it makes sense. It makes sense. It's like GIF versus GIF.
Yeah, I don't know what to go do it there.
Yeah. So up until now, we've just been using some the inbuilt data structures in Python. This is not inbuilt, but it's a module that we load into our Python environment. So we import NumPy as NP, and we also import matplotlib pyplot as PLT. So NumPy is basically the de facto standard in Python for handling large numerical data structures. And matplotlib is the de facto standard for plotting. Okay. So yeah, let's delve into this. So in NumPy, you create an array, and I've defined an array is equal to a NumPy array of numbers between 0 to 6. And we can print that. Oops, I haven't actually run that cell. There we go. Remember, you always have to, while you can kind of go back and forth a little bit in these Jupyter notebooks, you might have to run, if you restart, if your kernel crashes or, something goes wrong, it's always useful to run it from the top to bottom, because, then all the variables get stored back in memory again. Okay, so we've imported NumPy and matplotlib. Perfect, we've got our list. And so this is a NumPy list, and there's lots of cool things that we can do to it. So we can query what its shape is. Yep, it's 7 elements long. What else can we do? We can reshape it. So at the moment, it's just a 1D list. We can reshape it to we can reshape it into a whole bunch of rows instead of columns. Yeah, we'll kind of explore more of these a bit later. Another data type that we commonly encounter is kind of like a matrix of numbers. So here we've defined A as equal to a 4x4 array of zeros. Okay, so if we run the cell and print out A, there's four columns and 4 rows of zeros. We can print out the shape of A, and yep, no surprises here, it's 4x4. And we can also apply indexing to A as well. Yeah, so remember before we had our indexing where we wanted the first Where was it? It was here. Yeah, we wanted the third item in times. Or we can do exactly the same thing down here with NumPy, where we have the 0th row and the 0th column of A. And we're just going to assign that to equal 2. Okay. And then that's exactly what happens here. So we can change this up again as well and say, okay, we want the first row and the first column of A to equal 2. And it gets moved down here. We can also do indexing and broadcasting. So here we're printing out where A is greater than 0. I'll just run that cell. And no surprises, where A is equal to 2, there's a true, and everywhere else there are falses. Yeah. We can also print out, so that, you know, this is giving us an array of trues and falses. NumPy where is asking exactly which indices are they where A is greater than 0, and then this is the row index and this is the column index, and it's 0, 0, unsurprisingly. Okay, and then we can also do other stuff, like we can make B is equal to A times A, or A squared, and we can mask all elements of B where A is equal to 0 and assign them to 1. Okay, and this is the printed out here. So our A matrix was squared, so the 2's the 2 became 4, and all of these were 0. But then down here we've assigned all of the 0's in the B to equal 1. We can also do some nice vector operations. So here we're creating another array called X, and X is equal to a range of numbers from 0 to 2 pi with a spacing of pi over 10. And then we've got S is equal to sine of X, C is equal to cos of X, and I've thrown this one in here too, C2, which is equal to the gradient of S with respect to X. So let's print this out using matplotlib. So it's very simple. We plot our x-axes, our y-axes, and I've just given the label here. So in this case, sine of X. Now what we can see is that we have a nice sine curve here for sine of X. We have a nice cos curve for cos of X. And this dashed line here is our derivative of sine of X, which unsurprisingly is cos of X. Yeah. So isn't that good? We can do calculus without having to know any calculus at all. We can just ask for NumPy to give us the gradient of a curve, and it'll just chuck us out the derivative. So we don't need to rediscover high school maths to enjoy Python. All right. Any questions on this so far? Feel free to reach out into the chat or unmute. Happy to answer any questions. This is like 2 years of remote teaching has taught us, like no one leaves on their camera or their microphone, except inadvertently, and then you hear like strange animal sounds coming from the kitchen. All right. Well, if there's no questions, then we might move on to SciPy. This is probably the second most common library that we import in Python. And in this case, so SciPy is actually huge, right? We can, let's just type in SciPy into DuckDuckGo. Let's see, I just want to find the API documentation, API reference. Yeah, okay, so look at all these different modules here. there's something for everyone. There's clustering algorithms, there's fast Fourier transforms, there's integration, interpolation, linear algebra. Yeah, the list goes on. It's a huge scientific package for Python, and it's amazing, right? Because all of this has been developed and maintained by mostly volunteers. So this is a fantastic community effort, and I think we should acknowledge that. Python wouldn't be as good as it is without the contributions from thousands of developers across the world. All right, so we saw that bafflingly long list of different modules you can import from SciPy. In this case, we're just going to play with the interpolate one. So from SciPy interpolate, I'm importing this function here. So I'll just run that. And now what I've got here is I've defined X as a list of numbers between 0 and 10, with a spacing of 11 points in between. I've defined Y is equal to a function with respect to cos of X. And I'm constructing a whole bunch of different interpolants, okay, using this interp1d function. So interp1d takes in X and Y, and you specify what kind of interpolation you'd like. I should also point out at this point, I just want to create a new cell, so I'll do that here. If you go help and interp1d, then you'll get a nice long help documentation, which tells you, okay, what sort of arguments can you pass to this function? And, so it's got parameters here, what they look like, and what it returns as well, and some examples here too. So yeah, it's really nicely documented. Okay, so we've constructed our interpolants in this cell. Boom. Now what we might do is plot each of those arrays. So I'm plotting X and Y, which is our input data. I'm plotting F with respect to X new, which is this new array of numbers that we want to interpolate to. So we've taken our input data and we want to increase the resolution using X new. And so F of X new gives us some interpolated Y values, and we repeat that for the different kinds of interpolation. Yeah, and then let's just run that. Okay, and so we can see quite clearly what's going on. So when we had linear interpolation, yeah, we get basically a straight line connecting each of the points. If we get cubic interpolation, then we have a high degree polynomial that passes through each of these points. So we get a nice smooth curve. And if we choose nearest neighbor interpolation, then essentially it's like a stepwise function. So we get halfway between this point and the next point, and we get this steep step occurring. Cool. Moving swiftly along, because we're going to run out of time for pyGPlates. This is concerned with loading data. So you won't be able to see the course data here because it's hidden in behind the scenes at EdSTEM. But you can access these data by looking at the GitHub repo and in this data folder. So this is everything that we'll be using today, all the data that we have. But yeah, on EdSTEM, we refer to the data within this directory. So let's say we have some data. This is some EarthChem data with copper concentrations across the globe. So to load these data into Python, we can do it a number of ways. This is probably the easiest one, numpy.loadText, because actually if we open this up, yeah, it's just a regular CSV file. So we've got latitudes here, longitudes here. I believe this is the age of the deposit, and this is the concentration of copper, I believe. Okay, so we can just load that in, specifying our delimiter, which is commas, because it's a comma separated file. So let's run that cell, and then we can kind of probe what the data looks like. So we can print it out, and there we go. We've kind of truncated it here because it's so many rows. So, you know, it's got a dot, 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 and then it's gone down to the last 3 rows. We can print out its shape. So it's 207,000 rows, 431, 207,431 rows and 4 columns. Cool. And we can also plot these data. So we know that the first column is the longs and the 0th column is the lats. So we can do that, and yeah, it looks like we've got some spurious data here. As the text says, this does not look right, and that's because it's a messy data set, and that's not uncommon. Maybe the lats and longs are stored as eastings and northings for some reason. Maybe they're missing a decimal place. Anyway, let's clean this up using Python. So we can enforce everything to exist on the global extent. Remember that everything in Earth sciences is between negative 180 degrees, positive 180 degrees, negative 90 degrees, and positive 90 degrees. That's the global extent. So let's just filter out any samples that don't fit within our global domain. What I'm doing here is just copying the data just so that I don't muck anything up. And then here, I'm subsetting chem data so that I'm only interested in longitudes that are greater than negative 180 and less than positive 180, greater than negative 90 and less than positive 90. Okay, so let's run that cell. Cool, we have removed 47 samples. So now if we go to plot this again, that's looking a lot better. Cool. And now we can plot this on a nicer map or nicer axes. So here I've set up my figure. Figure is equal to plot.figure, and I can specify the figure size and the DPI, which is 150. This is plot.scatter, so this is creating a scatter plot. We've got our X data here, our Y data. The size of each point I've scaled by its age, and the color I've made equal to the copper concentration. And then I've just specified a Vmin and Vmax so that, you know, we can kind of restrict the range of copper concentrations that we're interested in. And helpfully, matplotlib has a color map called copper. That's so good. We can also check out all the other available color maps here. Wow, look at them all. And I spent a little bit of time on this because it does a really good job of showing, I guess, how colorblind friendly some of these are. I think it does. Yeah, here it is. Yeah. So these so-called perceptually uniform sequential color maps, you can see they have a nice gradient, constant gradient from dark to light to represent data values. Whereas some of these other color maps don't do nearly as well. But most of these are pretty good. But if we go down to some of these legacy color maps here, like HSV, that's just horrible. We've also got jet somewhere. Yeah, there it is. There's jet. Yeah, so it's a bit disgusting. So that's not a colorblind friendly color map. Friends don't let friends use jet. Incidentally, rainbow is slightly better, but not that great. Turbo is probably slightly better than that again with rainbow, but yeah, it's not good if you're displaying sequential data using a jet color map, because it's actually a diverging color map, really. So yeah, a better choice is some of these perceptually uniform ones up the top. The default in Matplotlib now is Viridis. All right, let's go back to our workspace. So yeah, we can plot this. Takes a little moment, and there we have it. Now this is nice, but we can actually make it look a whole lot nicer by using a mapping module called CartaPy. So CartaPy is great. This is just a stock standard map. So we create our figure as normal. It's exactly the same as above here. Create our axis. And the secret here is that we're passing a different projection. So this projection keyword is equal to this CCRS dot plate query. So that's the map projection type. Down here, I've set the default as global, so it hugs a global extent, and it's got this inbuilt stock image, which is just the I think it's the natural Earth elevation image, and we've also got the coastlines plotted on there for good measure. And like in GPlates, you can change this so that you have the central longitude equal to 180. Yeah, and then we get the opposite meridian being the central one. So we can see Australia a bit more nicely, as it should be. And then we can, so we've got our standard map axis here, and then we can just add some data. So we can just plot the same scatter plot that we used before. This is exactly the same line of code, except at the very end, we've got this transform keyword, and then we've transformed the data. We're telling CartaPy and Matplotlib what sort of projection the input data is, and that's just generally the plate query projection. Cool. So now there's like another little exercise. Yeah, we're probably not going to get onto pyGPlates, much of pyGPlates today, but yeah, another little exercise to change the projection type to something else. So what I suggest you guys do is click on this link, and you can see, here at the top is plate query. You've got a whole bunch of other projections available to you in CartaPy. So, there's the Mercator projection, that's pretty common. We've got mole-wide, orthographic, Robinson, and then you start to get some pretty obscure flavors the further down we go. All right, so there's some rotated poles. There's a European projection, near side perspective, so it's like a satellite just slowly zooming in onto the Earth. Yeah, some pretty weird ones coming up. Yeah, one of Ireland. Don't know why that's there. Maybe the person who developed this was Irish. And we've got, South Polar stereo, so this is good for polar or Antarctic regions. And yeah, so just try that in your workspace. I'll just do it again here so that you guys can see what I'm doing. So if I just change this, whoops, to multi. Why did that go all the way to the top? There we go. That looks pretty nice. Again, we can change central longitude to 180. It thinks about that for a little while. And there we have it. All right, and there's also Robinson. Yeah. So yeah, it looks good. And, you know, we don't have to do any tricky importing, exporting into GMT to create these maps. We can do it all from Python, which is really nice and powerful. Okay, we have 9 minutes left. Sorry, Nicky. Yeah, I hope that was kind of a nice primer to Python and some of the common libraries that we'll be using. I haven't been paying attention to any of the discussion board. Let's just see. GitHub link. Thanks, Nicky. Yeah, no, everyone's very happy with that. That's good. All right. Okay, let's go back into our workspace again. So the next notebook is getting started with pyGPlates. Maybe I'll hand over to Nicky for the last 9 minutes, just to maybe talk a bit more about pyGPlates, and I guess we can talk a little bit about importing and reconstructing features.
Yeah. Do you want to continue sharing your screen, or do you want me to share my own screen? I'm happy for you to.
Oh, yeah.
Or you can share it, and I guess you can look at my notebook if you wanted to. Okay.
I've stopped sharing.
Yeah, I've just noticed. Okay, I think this is it. So can everyone see my screen?
Yeah.
Okay. I'm just going to move that out of the way.
So now it's just it's a white line on my Zoom for some reason. Maybe you need to reshare. Yeah, that's weird.
I have multiple monitors and everything is going everywhere. Oh, my screen sharing is paused. Just gonna, sorry, plug that. Okay, see that? So, yeah. So for pyGPlates, there's been a lot of development, and back when I did my honors in my early parts of my PhD, this didn't exist, and it makes life so much easier. So it's a little bit of a pain to install if you haven't, if you're not a Python whiz. A Conda environment is coming soon, a Conda package, but we've set up this so you didn't have to run into installation issues straight away. And so the first thing you need to do is, test that it's actually installed correctly. So if I import pyGPlates, it doesn't complain. So it's imported correct. It's all installed correctly. And to actually use pyGPlates, we need to load in some files. We can define some files in the notebook itself, but generally we'll probably want some kind of rotation file. And you're probably not going to make a rotation file within your own notebook. You probably have it somewhere on your computer already. So in the first example here, what we'll do is we'll import a rotation file, and then we'll create our own points, and we'll reconstruct that to some time in the past. So most of the data that we've got here in this course data folder is from the GPlates 2.3 sample data. So you'll have these all on your computer already. And so you can see here, I've just specified my rotation file, and then I'm creating a list of points. So I've chosen longitude, latitude of Sydney, and longitude and latitude of Melbourne. And I already know their plate ID in advance. They're both in the Australia plate, so it's 801. And then we create our point feature. So pyGPlates won't know what this point is until I can copy all of this into a new thing. So you'll see if we just print out points, we've just got, the longitude and latitude of Sydney, longitude and latitude of Melbourne, rounded to 1 decimal degree, 1 decimal place. And so to get points into pyGPlates itself, we need to create a pyGPlates feature, and you'll find this features quite a lot, this pyGPlates feature. So what we'll do is we'll go through, we'll loop through our little points that we just printed out here, and then set the latitude and longitude as the first two elements, and then the plate ID will be the last element. And so we'll set geometry, this little function here. And because we've got, these are points and we want to visualize them on a sphere, we'll tell pyGPlates to create that latitude and longitude as a point on sphere type. And so sometimes a little bit annoyingly, pyGPlates likes to deal things in latitude longitude space, so x, so y then x coordinates rather than x and y, like many other programs do. So just be aware sometimes you need to flip your y to be the first number. And then we'll set our reconstruction play ID as that the third number in our little list there. We'll create that little feature. So if I do this, now this will all be saved into this point features, and you'll see we'll print out, it looks a little bit like gibberish. You can't see your nice longitude and latitudes anymore, but now pyGPlates is ready to use it and it knows what's happening. So the next step then is we can define a reconstruction time and then actually reconstruct that to some time in the past. And so you can't really see, the wrapping isn't great here, but there's this function pyGPlates reconstruct. And so I think I've got a link in the document in here somewhere, or one of the notebooks, to the documentation. But this little function takes input of point features, and it takes a rotation of whatever your points are, whatever your file is, takes a rotation file name or a rotation model, and then it will save everything from it into whatever this third argument is, which in this case I've created as an empty list called reconstructed feature geometries. And you actually save directly out to a shape file here if you wanted to, or to a GPML file. And then the last number is what time you want that reconstruction thing to be at. So this, in this case, it will be at 40 million years ago. And so if I run this, we can't just, if I have a look at what's in this little reconstructed feature geometries, it's more pyGPlates kind of gibberish, if you want. So it's hard to see exactly what it's done. So then you'll find that pyGPlates has a lot of looping through things. And so you'll find to get the actual coordinates back out so we can print them nicely, that I do at the bottom of this next cell, we have to loop through. So I go through for each element in this little reconstructed feature geometries, and I get their reconstructed coordinates based on, I have to get this reconstructed geometry, and then I can convert that to latitude and longitude. And again, latitude and longitude is first in this list. Because pyGPlates has reconstructed it, actually knows what the present day geometry is as well. So I can also get that here using get present day geometry, and then I can convert that into latitude and longitude that looks a bit more sensible for everyone. And then here I've just got a print statement. So it will print out the latitude and longitude of the present day, and then latitude and longitude of the ones in the past. So when I run that, you'll see that, our point at, so this would be Sydney at present day, 40 million years ago, it was somewhere further south. So it would have been a lot colder for me. And that's probably enough for today, because I guess we're back right on 11 a.m. But then tomorrow we'll start getting to some of the more exciting stuff. So we can, if you don't know your plate IDs in advance, we'll need to assign them. So we'll start doing that. And then we can also reconstruct and plot some coastlines. So there's no pictures. Oh, there is a picture here. So you'll see, we'll make this image using some CartaPy that Ben just introduced on a lovely Robinson projection. And we can also anchor plate IDs, and we'll kind of get more and more complicated from there. But there's should be something for everyone if you're a keen GPlates user. Does anyone have any questions? No?
Thanks, Nicky. That was a really good 10-minute intro to feature types. Loved it.
Yeah. pyGPlates is, it gets a bit confusing, but like once you kind of get into the rhythm of it, it's not too bad. And for me, I personally find I just copy and paste a lot of code that someone else has already written, and then just change some inputs and change some outputs. And it all seems to work magically. So I highly recommend looking at, if you ever want to use it and you have no clue what to do, it's great looking through the GitHub for Earthbyte or the GPlates GitHub, because there's some tutorials on there as well. But you'll find it will be a lot of looping through files to then eventually get out a geometry or a reconstructed coordinate or a plate ID or some other attribute. And you can make little functions to make this a little bit easier.
Yeah, definitely. All right, well, yeah, maybe we'll wrap up there. So thanks everyone for joining the pyGPlates component and the GPlates component on behalf of Sabin. We'll see you at the same time tomorrow.